Question number 4. If you mix 2 liters of 1 molar NaCl solution with 1 liter of 3 molar glucose solution, what is the osmolarity of the resulting solution? This is a type of question that's listed in one of the 6 benchmarks at the beginning of the class. The essential part to solve this question is to understand when you mix 2 solutions together, or even more solutions together, what is changing and what remains unchanged. Let's take these 2 solutions as an example. When we mix a 2 liters of solution with a 1 liter solution, they have different solutes and they all have their own molarity. When you mix them together, the total volume of the resulting solution is going to be bigger than any of the original solutions. So the molarity of each of the solute from the original solution is going to be smaller because when the volume becomes larger, it's a dilution for each of the components of the original solution. But what remains unchanged during this process is the amount of particles, the moles of particles, or the weight of the molecules when you mix the 2 solutions together. For example, the moles of NaCl that you have in the original solution will remain unchanged even when you mix it with another solution. Since we know that the moles of NaCl and glucose will not change during the mixing process, let's solve for the moles of NaCl and glucose first. The moles of NaCl in the original solution equals to the molarity times volume, which is 1 molar times 2 liter, which gives you 2 moles of NaCl. That's the amount of NaCl that you have in the original 2 liter of 1 molar of NaCl solution. And no matter how you mix that solution with other solutions, the amount of NaCl that's been provided by this solution will not change. So 2 moles of NaCl will show up at the new solution. Similarly, you can have the moles of glucose, 3 molar multiplied by 1 liter, which gives you 3 moles of glucose in the resulting solution. So now we have the moles of each component of the new solution. We can calculate for the molarity of NaCl and glucose. We have the moles. We need to know the volume of the solution. If you mix a solution of 2 liters if you mix a solution of 2 liters with a solution of 1 liter, the total volume of the solution will come up to 3 liters. So the molarity of NaCl in a mixed solution in the resulting solution is going to be 2 moles of NaCl over 3 liter. That is the total volume of the resulting solution. So in the end, it gives you the new molarity of NaCl in the mixed solution as 2 over 3 molar, 2 over 3 moles per liter. Similarly, you can have the molarity of glucose in the mixed solution with a number of 1 molar. Okay, with the help of this preparation work, we already know what the molarity of NaCl, molarity of glucose in the new solution. Then we need to find the osmolarity of NaCl and glucose, respectively. And then we can simply add them up together to have the total osmolarity of the resulting solution. And that is the final number, 2.33 osmolar. So the key part to this question is to understand that you can simply use the old molarity to calculate for the overall osmolarity of the new solution, because when you mix 2 solutions together, the solution, each of the solution will be more dilute than the original one, so the molarity will be lower. You need to get the new molarity and to calculate for the new osmolarity of the resulting solution, and then you can add them up together. Part B of question number 4 is a statement. it is possible to compare the osmolarities of any two solutions simply by comparing their concentrations in osmoles per liter. The key word to this statement is colligative properties. Since osmolarity and osmolality are colligative properties, they're closely related to the osmotic pressure of a specific solution, and they only care about the amount of particles there are in a solution instead of the types of particles there are in a solution. That's why we can simply compare any two solutions, even with different solutes in them, by comparing the numbers of their osmolarities to tell which one has a higher osmotic pressure. With that comparison, you know that if we connect these two solutions with a semi-permeable membrane, where will the net water movement go? Where will the direction of osmosis go? This is in comparison to the non-colligative properties, such as molarity. Let's think about it. When you have two solutions with different solutes in them, with different molarities, let's say when you have 1 molar of KCl solutions in solution A, and when you have 1.5 NaCl in solution B, simply by comparing the numbers of 1 molar and 1.5 molar, you can't reach any conclusion, unlike the colligative properties such as osmolarity. Knowing all this, we can move on to a new set of concepts called hyper-hypoisoosmotic. When we have two solutions, solution A and solution B, if solution A has a higher osmolarity compared to solution B, we say that solution A is hyperosmotic to solution B. And at the same time, solution B is hypoosmotic to solution A. If solution A and solution B has the same osmolarity value, then we call these two solutions isoosmotic. Note that hyper-hypoisoosmotic is reached simply by comparing the values of osmolarity of two solutions or osmolality of two solutions. It's not related to anything else, just simply compare the osmolality or osmolarity values, and then you can reach the conclusion of which solution is hyper-hypoisoosmotic. Our next slide is a question. Hyper-hypoisoosmotic are used to predict the process of choice A is osmosis, choice B is diffusion, choice C is both of them. You can take a second and pause the video to think about it. Hyper-hypoisoosmotic, they are terms simply as a comparison between osmolarity of two solutions. So if one solution has a higher osmolarity, doesn't mean it has to have a higher osmotic pressure. Doesn't mean it has to have a higher concentration of a specific ion that's related to the diffusion. Okay, so the answer is A, is osmosis. Hyper-hypoisoosmotic are only used to predict the process of osmosis. The reason being that this set of terms is only a simple comparison between the values of osmolarity of two solutions. And osmolarity is directly related to the osmotic pressure. Osmotic pressure is directly related to osmosis. So osmosis is dependent on this set of definitions, this set of concepts. But diffusion is very different. Diffusion is not related to the overall concentration or overall osmotic pressure of a specific solution. Instead, it's only related to the concentration of the specific particle that you are looking at. If you're confused at this point, please go back to our original very simple model, very simple scenario, and think about this model. So these two solutions, solution A and solution B, they both have an osmolarity of 4 osmolar. So I'll say solution A and solution B are isoosmotic. From the term isoosmotic, the only thing that I can know is there's no osmosis happening between solution A and solution B. But can I say that there's no diffusion since they're isoosmotic? Certainly no, right? Because you know that if you want to look at the process of diffusion, you only look at the concentration of the specific particle that you're looking at. For example, if you want to look at sodium ion, the diffusion of sodium ion between solution A and solution B, you should look at the concentration in solution A is 1 molar. The concentration of sodium in solution B is 2 molar. So sodium is going to move from B to A. That's the diffusion of sodium ion, a specific ion. So it's irrelated to the overall concentration of these two solutions, and is irrelated to the osmosis process of the two solutions. That gives us one of the most important slides of this class. What parameters do we use to predict the direction of osmosis and the direction of diffusion? Osmosis is a process simply only related to the osmotic pressure. So osmolarity is the only parameter that you are going to look at when you want to tell the direction of osmosis. The direction of osmosis is going to be from a lower osmolarity part to a higher osmolarity part. Very different. The process of diffusion is only related to the concentration of a specific particle, is irrelevant with osmolarity, is irrelevant with the overall osmotic pressure of a specific solution.